So yeah, this is a talk about the type theory, the axiomatic system that lean depends on, and some properties about it. So lean, most of you I think already know this, but lean is an open source interactive theorem prover developed by Leonardo de Moura from Microsoft Research, and his work is also being extended here at CMU and at Pitt. And so there's a focus on software verification and formalized mathematics. Well, not so much with software verification right now, but at least some programming and meta-programming capabilities in this functional programming language Lean. It's based on dependent type theory, and that's going to be the main topic here. So it's a classical, as opposed to intuitionistic, not a homotopy type theory based system. It's very similar to CIC, which, depending on who you ask, is the axiom system that Cuck uses, or is some idealized version of the axiom system that Cuck uses. But anyway. And Lean 3 also has some metaprogramming facilities and a active development for the MathLib library, which is just developing pure mathematics and tools for programming and metaprogramming. Okay, so so we start with the untyped lambda calculus. So here is a very simple display of what's happening in the lambda calculus. So the top line here is saying that an expression, E, is either a variable or an application, that's just the adjacency of two expressions. So we have an expression applied to an expression, or we have a lambda, and that binds a value x inside the term E. And it has these reduction rules. So what I'm giving here are the non-deterministic reduction rules, where you just go into each application, or you go somewhere into an application, and you beta reduce, and then you apply this over and over, and you get somewhere, or you get multiple places over nowhere. And so that's basically how reduction of the lambda calculus works in a nutshell. It's developed by Alonzo Church as a simple model of computation. This is equivalent to Turing machines in power. There is some stuff I haven't mentioned here about how exactly substitution and bound variables are defined, but the details of that are mostly the same as any other system involving bound variables. So yeah, I won't go into that right now unless someone asks. So there's a primitive notion of bound variables and substitution, and this reduction operation is the non-deterministic one. There are restrictions of this where you can say, well, it's called by value or it's called by name, depending on how exactly you do these reductions. But here we're just saying, all the possible reductions. The reduction is confluent. So this is called the Church-Rosser theorem. This is important. We're going to come back to this later. So if you have an expression which can reduce in 0 or more steps to E1 and also to E2, then there's another term, E prime, such that they both reduce in 0 more steps back together. So even though there might be sort of an infinite sequence of steps going off, you can always bring two terms that have started from a common term back together. So we're going to extend this a little bit, or we're going to add in a type system on top of this lambda calculus. So now the main difference is that our lambdas have a type annotating the x, and the available types here, I'm just keeping it very basic. We just have function types and then some base type of individuals. And this is really, we don't really need the individuals, except that if we took it out, then there would be no types at all, and so there wouldn't be anything in theory. But yeah, okay, so we have rules here for the typing judgment. So I've left off the rules for reduction, but they're exactly the same as the last slide. So here we have, this is a variable rule. This is saying that, so we read this as, in the context gamma, x has the type tau, assuming that we have in the context that x has the type tau. So this is just the variable rule. It's just looking somewhere in the context for x has the type tau, and then we can type check it there. And then this rule is for how to check a application. So if you know that E1 is a function which has domain alpha and codomain beta, and E2 is a value which has type alpha, then you can apply E1 to E2, and then you get something type beta. And then over here we have the rule for lambda. So a lambda is a function type. So it has type alpha to beta if in the context extended with x having the type alpha, E has the type beta. So this is enough for you to be able to type check some simple terms. And interestingly, unlike the untyped lambda calculus, here we have, just because we have this typing system, we get that all terms normalize. So this property is called strong normalization. And so there are certain terms, like the y combinator, which I haven't written, which you can write down in the untyped lambda calculus, but have no valid typing in the in simple type theory. So they're just not available anymore, and those terms would unfold forever if they were in the system. So this is excluding them. Okay, so now we want to go from this to dependent type theory. So the first change is, well, let's say we have this function type, and I want to say, okay, I want the first thing to depend on the second thing. So I'm going to replace that. Oh yeah, so this is just rearranging them. But I'm going to replace the arrow type with the for all type. And so it looks very similar. We have a for all here instead of a, and this is also called the dependent pi. I'm going to use for all in these slides, but just treat them interchangeably. So here we have, instead of alpha arrow beta, we have for all x and alpha beta, and this beta here is allowed to refer to x. And then the rule for application involves a substitution for the x's and beta. Now, we can't really do that much interesting with the with x inside tau, because tau doesn't actually have any operators to be able to put x's in there. First, we're going to go, oh yeah, so first notice also that x has to vary over a type, tau, and one of the common applications of this is if we want to have for alls which are sort of parametric. So if we wanted to write the parametric identity function, we might want to generalize of a variable which is actually a type. So in order to do that, we need a type of types. And so I'll call that u, and so we'll add another type u. And then we can just sort of add rules that say, oh yeah, all those other guys, those are types. So iota is a type, and this for all is a type if its parts are, and type is a type, okay? And actually, so at this point, we don't really need to have two separate classes anymore, and this is where we actually get most of the power from, is by just sort of folding the tau and the e together. So we have, instead of having a collection of terms and a collection of types, we're now just going to mush everything together. So we just have expressions which can be terms and types. And so now it's all the rules are exactly the same as before, but now it's just one big soup of things. And so now we can talk about lambdas which have results which are types. And this allows you to do sort of computations at the type level. So this really gives you some extra power. Okay, so there's two problems with this as I've written it here. Oh yeah, sorry. And also, we don't really need this iota anymore because we've got plenty of types now, so we're just going to drop it. And so, okay, so two problems. So first of all, that rule there is inconsistent. So if you have, if you know that type has type, then you can construct a slightly more complicated version of Russell's paradox in the system, and you can show that basically all propositions are inhabited, i.e. all things are provable. That's not good. So in order to solve that, we can sort of break this circularity by saying, okay, actually there's a whole hierarchy of universes. We have that the universe at level n is a type at universe level n plus 1. And then we're going to have a rule for the pi that says that, well, if you've got two different universes, then when you make their pi, you get one in the larger of the two. So this avoids you populating things at an unusually low level. Okay. Now, that's also not quite what we want. So this is not really doing the topic justice, but I'm just going to throw up here the Curry-Howard isomorphism, or the Curry-Howard correspondence, which is basically this idea that propositions act a whole lot like types, where the terms of that type are the proofs of that proposition. So that false propositions are going to be empty types, and the provable propositions, we're going to have maybe one or more ways to inhabit those types. And so that's actually why we're using the arrow and the for all symbol here, because it is actually, it acts just like what we would want material implication and the for all quantifier, like in first order logic. This acts just like that. So we're actually going to have a universe of propositions. So in order for this to work, we're going to say that that for all is a proposition, and that means that it has the type U0, which here I'm going to denote as P. So this is the universe of propositions. But now if you look at this rule before, I said that, well, if you've got um and un, you get the max of m and n. So if this one here is 0, then this is going to be m. And so if we take some example propositions, so I haven't given all the things in order to define what even or odd means, but let's suppose we can define this thing. This is a proposition, it's in U0. We have natural numbers. This is a type, it lives in U1. And so when we stick them together to form this particular proposition that says every natural number is either even or odd, then we end up with something in U1. And this isn't quite what we like. I mean, we want this to be some kind of proposition which is just talking, it's either true or false. We like to think of it that way. And so having it end up as a type seems a little bad. So we're just sort of going to add an extra rule. We're just going to fix this rule so that instead of using max, we're going to add this weird imax function instead, which is the same thing as max, except when n is 0, it's just going to be 0. And so we're just saying, well, okay, fine. In this case, it's 0. It's not 1. So this is called impredicativity. It means that you can construct objects sort of at a high, in a high universe, and then sort of reflect them back into this lowest universe of propositions. So this actually adds quite a lot of power to the language, axiomatically. Okay, so this is where we're at. So now we have this IMAX and levels of universes. And now, so problem number 2 is that we have convertibility issue. So we have the ability to form the type, we have the ability to form a type, which is the identity function applied to tau. And that's not the same thing as tau itself. And so you can have not well-typed applications where you have a function whose domain says identity applied to tau, and you're applying it to an argument which has just type tau, and that's just not going to type check. So we'd like to be able to type check those, especially when we have some kind of reduction rule like this. And so the solution is to have a convertibility judgment. And so we're just going to say that well, if alpha and beta are definitionally equal, then anything which has type alpha also has type beta. And that comes with a whole bunch of rules. These rules are fairly self-evident. So these three are saying that convertibility is a equivalence relation, so it's reflexive on well-typed terms, and it's symmetric and it's transitive. These rules are just saying that it has it just goes through all these are compatibility rules. Yes. So these are called compatibility rules, and they just say that as long as all the parts are definitionally equal, then so are the whole terms. And then these are the rules that actually have some content. This is the beta rule. It's exactly the same as the reduction rule from before, but now it's just being stated as a definitional equality. And this one is called the eta rule. It says that if E doesn't depend on X, then if you have a lambda applied to an application like this, this is the same thing as just E itself. So this is called the eta rule, and we also have a rule for that. So the last major feature in this axiom system are inductive types, and this is one of the more complicated features. So we want to have a general mechanism for defining a bunch of new types. And so I'm not going to give the typing rules because they're complicated, but the syntax at least, I'm going to write it as, so K here, I call it an inductive specification. It's really just a disjoint sum of labeled expressions, and these labels are the constructive. So I have a bunch of examples here. So the natural numbers are, so we read this as, this is the fixed point of the function which takes a type and is either an element of that type or an arrow from the type to itself. So 0 is in the natural numbers, and successor is a function from the natural numbers to the natural numbers, and then the natural numbers are sort of the smallest type, which has these two functions, and which is freely generated by them. So I'll show how the recursors are done in a second. So I just want to give some examples here of the sorts of things you can do with an inductive specification like this. So here's the sort of the rest of propositional connectives. So you can do exists by defining it as an inductive type, where you have a sort of a dependent introduction here, where you say, well, you've got an X, and then you've got a proof that P is satisfied at X, and from that you get an element of this exists, and because it's the smallest thing, you also get the ability to prove facts by cases on exists. And then and can be defined as one where you have an introduction which has two arguments. So you have P and Q, and from that you get the P and Q. For or, you can either have a P gives you a P or Q, and a Q also gives you a P or Q. Bottom, or false, is the proposition which has no constructors, and true is one which has exactly one named constructor. So each inductive type, when you write down one of these inductive types, you get the type itself, that's this mu thing, and then you also get the constructors. And so these constructors are just formed by taking those expressions there with the t and replacing t by nat. And so you get the 0 is a nat, and suck is a nat arrow nat. And then you also get this recursor. So this is generated based on the form of this description, on the form of this inductive specification. And in this case, it's saying that, well, if you have a dependent family over natural numbers, such that you have an element at 0, and then given an element at n, you can produce an element at suck n, then you get an element of Cn for all n in the natural numbers. And so this is really the one that's going to give you ability to prove that this is sort of the smallest type, which has those two, 0 and successor. And then this thing also comes with these so-called computation rules. These are actually reduction rules. I haven't written them like that because these are both definitional qualities, but also reduction rules. So you can reduce this thing where you apply 0 to the first argument. That'll be the C0. And then if you apply this function, so here we have C and Z and S, and then here we're applying suc n. And so this is just S, which is this function here, applied to n and to the value of the recursive. So this looks a lot like primitive recursion, and using this where you replace I with 0, you end up with a rule in prop, which is allowing you to prove things by induction on the natural numbers. So if you view it like that, then this is just the P&O axiom of induction.
All right, let me just remark that. So I think a lot of people here are kind of comfortable with this, but I'm really curious about the features of the mean that are, so keep an eye on the time that you're going to get to the good stuff.
Yes, almost there. Okay. There are some caveats on exactly what specifications are allowed. An inductive declaration has to be strictly positive, which basically means that you don't have this T appearing on the left side of one of these arrows. So an example of where you can get into trouble if you don't have a rule like that is this bad definition here. If this thing were allowed, then you would end up with a function, an injective function from the power set of bad, or bad arrows 2 here, 2 bad, which would be a violation of Cantor's theorem. And so since you can prove Cantor's theorem, you'd be able to get a contradiction from this. So inductive families are also allowed. So this is how equality is defined. So you just have, given an x, you can define equality to be sort of the least type which is inhabited at x only. And so you end up with a constructor REFL which says that x is equal to x, and then this recursor for EQ is saying that this is just a substitution property for equality. If x is equal to y, and c holds of x, and c holds of y. Proof of relevance is this idea that if we have two proofs, two elements of this lowest universe, then they are just definitionally equal. And this has some interesting consequences. So one of the things is that this is a anti-hot axiom, we could say. This is in contradiction to univalence, so we can't do hot with this. But it also means that propositions are going to actually have restrictions on them. So when you create an inductive type, which lies in prop, and which has sort of many ways for it to be inhabited, then there's going to be a restriction on the recursive that says you can only eliminate this into the lowest universe, into propositions. And so this would be called a small eliminating type.
So you said that this is in contradiction to univalence. Is it actually in contradiction, or does it just lead to a degenerate?
If you assume univalence, then you can prove that there are types which have more than one inhabitant for their equality, more than one unequal inhabitant. So it is in contradiction to axiom K, or to proof of relevance, or definitional proof of relevance.
So if you had univalence, you can actually derive false.
Yes. Yeah.
Are both P and U0 exactly the same? Or
Yes. Yeah. So I.
Okay.
Yeah. Okay. So the other interesting property is that there's an out here. There's a way for propositions, things that are lying, inductive types that have been defined to be in the lowest universe U0, that they will still be able to eliminate to higher universes. The short description of when that will happen is if they have all of their non-recursive arguments, so the ones that don't end in t, those all have to be propositions, or else they have to somehow appear in the final type. So I didn't want to write that condition because it's a little bit complicated to state, but when it does happen, then you get what's called a sub-singleton eliminating type. So for instance, EQ here, this is actually a sub-singleton eliminating type. So you can recurse EQ into any universe, even though it's a prop. Okay. And so the actual axioms, so by actual axioms here I mean these are just objects that are added to the language and they have no interpretation. They're just things that are inhabiting various types. So propositional extensionality is saying that if P and Q are, if and only if Q, meaning that P implies Q, or there's there's an inhabitant of P arrow Q and there's also an inhabitant of Q arrows P, then P and Q are actually equal, which means that you can substitute for them in all contexts. This is kind of a weak version of univalence at the lowest proof at the lowest universe. Quotient types, I'm not going to deal with them too much, but they're given by you have a make and a lift and a rule. This looks a lot like a inductive rule, except it's not freely generated. It's generated up to this relation R, and then you can inhabit it when you know that the functions sort of preserve the relation R. And then the axiom of choice, well, so you can define this nonempty here to be just an element of prop, which is, I guess this is sort of the least element of prop, which is inhabited when alpha is inhabited. And then choice is just saying you can go the other way around. So if you have an element of non-empty alpha, then you can get an element of alpha. And this has no computational interpretation. This is just a thing which allows you to do classical mathematics. And from this, you can get the law of excluded middle. And so with this, it's really a fully classical logic.
I'm sorry, I don't understand the definition of non-empty here at all.
Okay, so non-empty is, so in lean, we would write this as so this thing is a prop, which is given a single constructor which says that if you have an element of alpha, then you have an element of non-empty alpha. So this looks sort of like an identity,
So
or
it shouldn't say intro colon alpha arrow T?
oh dear, I'm sorry. Yes, you're right. Okay. Yes, yeah, this is, yeah, that's a typo. This should be alpha arrow T. Yeah.
Is this different from the quotient of alpha by the total relation?
Yeah, because that doesn't tell you that it's non-empty.
Oh, it is.
Oh.
The quotient is not in U0. The quotient is not a prop.
Gotcha. Thank you.
So, yeah, MathProp actually has both definitions. There's non-empty and then there's trunk. So the quotient by the total relation is called trunk, and it's just
Great.
like the propositional truncation. And it doesn't lose information. Like, it doesn't put you into this world where all proofs are definitionally equal. So that makes a big difference.
Yeah.
And so the fact that choice is saying, oh, but you can get out of that, that's what really breaks the computational interpretation. All right. So one of the unusual consequences of all these axioms put together is undecidability of the type system. So this is a bit of a disappointment for type theorists, but basically the type judgment is almost decidable. But there's a way in which they can interact. And so let me try to sketch this situation. So consider this this inductive type act. And so this is defined as, well, basically, if everything is less than if everything less than x is accessible, then x is accessible. So it's inductively generated by that clause right there. And so this is basically saying that it's well found. The type is well founded. If everything is accessible in this sense, then the type is well founded. In general, you know, we're just talking about things which can be sort of reached from the bottom by things which are smaller, according to this relation less than. Importantly, this thing is a sub-singleton eliminator. So because the rules of Ling say that because this thing has this guy here is a recursive argument. This one is not a recursive. This for all x, this is x and alpha. This is not a recursive argument, but it appears over here in the target type, and so it's okay. So this whole thing is a sub-singleton eliminating type, and so when you ask me what's the recursor, it will say that this is a recursor which eliminates into any type, even though this thing is a prompt. Now, there's only one constructor, and you can sort of invert that constructor in the sense that if you have an element proving that act of x, then you can construct a function in the x which takes act of x and a y less than act of x and proves that y is accessible. And this will be in such a way that if you apply in, just as a result of the type of it, in A is of the right type to be applied to intro x, and this thing is definitionally equal to A because this is it's a proof. It's an element of a proposition, namely act x. So those two are definitionally equal, and that basically means that we can use it to do reductions repeatedly without sort of having to pay for them. Let me see if I can explain this. So let's suppose that we have a decidable proposition P, for all n P of n is not decidable. There are plenty of examples of this. Just like a Turing machine doesn't halt after n steps. You know, you can decide whether it halts or not after n steps, but you can't decide whether that's true for all n, at least not for some choices of machine. Okay, so suppose that we know that 0 is greater than accessible. So that's saying that 0 is accessible from above by the greater than relation. So this is not true, but we can put it in our context anyway. We can just suppose that it is true. We can derive false, but we can also derive some other things. So we're going to define a function by recursion on act greater x. So we can define a function for which it reduces in the following way. If you apply it to n and to h, you can replace this h with an intro of inv of h, like on the previous slide, and then we can set it up so that it reduces to this expression here. So we'll say, well, if p is true, then we're going to evaluate f at n plus 1. And then this is some proof. It doesn't really matter. Otherwise, it's going to be 0. So this thing will reduce to 0 if p is false. But if p is true, then it's going to reduce to sort of the next value. And so you can kind of see that this, if we sort of just pump this, it will reduce to, like if we start at 0, it's going to find out whether p is true, and if it is, then it's going to try the next value, and if it is true, it's going to try the next value. And if at any point it finds that p is not true, then it's going to reduce to 0. So this is really emulating, we're just stepping up the natural numbers, and we're trying this function f on all of the natural numbers. And you end up showing that under this context at h0, this inconsistent context, we have that this thing is definitionally equal to 0 if and only if for all np of n, which is exactly the non-decidable proposition.
You have that backwards, right? It's definitionally equal to 0 if there exists some n where p of n is false.
Oh, yes. Yeah, okay, yeah.
True to false.
Yes, false. Yes, just replace true with false.
Well, the even exists rather than a for all, but
If for all np of n is false.
if exists n p of n is false. Oh, sorry, yeah, I'm parsing it differently. Yes.
Yeah. If not for all np of n. Or maybe I'll just draw a line. Another thing which I want to mention is that you might say, well, kind of you're cheating. I mean, what's up with this inconsistent context here? Who cares about false context? Well, what we can actually do is just sort of lambda abstract both sides. We'll just say, well, lambda h x0, this thing, is definitionally equal to lambda x0 of 0. And those will be definitionally equal if and only if this is definitionally equal. So even though those are two empty functions, and they are kind of like, we should be able to treat them as equal, and we can prove that they are equal without the definitional equality, just regular equal. But they are definitionally equal if and only if this non-decidable proposition holds. So that's bad. Okay, so of course, lean can't evaluate non-decidable propositions. It does purport to evaluate this typing judgment. So what's it doing? Well, it does something else. It does. So we can introduce some new judgments just to say, you know, that thing that lean does that isn't quite what I just said, and that will be sort of an under approximation of the actual typing rules. So the algorithmic typing judgment is sometimes going to say this thing is not well typed, even though it really is. If you know, lean worked out that Turing machine's 10 steps, it'd find out that it is, but it's not going to bother with that. So in the example, so in this example, it'll just say, no, I don't believe you. Like, it's not going to bother evaluating that Turing machine. It's just going to say, no, they're not definitionally equal. And so there are times when it will sort of get the wrong answer from the ideal perspective. And as a result, you know, you can get that it can't be transitive. Like, if it were transitive, then you'd be able to recover the original thing. So the actual definitional quality, this weird example manifests itself in lean as non-transitivity of this definitional equality relation. In practice, is a really weird combination of features that no one ever deals with, and if it ever comes up, you can always sort of insert identity functions in order to sort of hide the non-transitivity. So if you want to, you know, get lean to see where that transitivity path is, you can just insert identity functions of different types, and then lean will be forced to figure out the smaller steps rather than trying to jump the big step. Okay.
Would that actually work in practice, though, since you don't have reductions? You might be able to find the term, but probably you couldn't use it.
Well, so you can always sort of write, like, I want to say, you know, E has type gamma, but it actually has type alpha, and I want lean to know that it has type gamma, but it can't prove that alpha is equal to, or alpha is definitionally equal to gamma. So I'll just add in, like, okay, this is an ID of beta of ID of gamma, and, you know, insert enough identity functions of different kinds that lean will be like, oh, I see where you're going with it. Like, it can figure out the smaller steps where it can't figure out the big step because it's non-transitive.
Yeah. So my question is, since you can't reduce one of those IDs, right?
Yeah,
Those-
yeah, if
they-
you reduce, so the property that reduction preserves typing is called subject reduction, and Lean doesn't have it.
So my question is, since I can't reduce those IDs, don't they serve as basically like a blocker that's gonna
Yes.
keep us from using this term effectively as an element of PM?
Well, so you can use it, you just have to unfold it carefully, basically. Like as long as you sort of control the ways in which you're unfolding it, you'll be okay. In practice, I think we just settled for like having a regular quality at some point because those tend to be a lot more stable. Like you can just not worry about how that's been proven. You just have a regular quality, and then it's not a definitional equality. You don't have to worry about the definitional equality folding. So that's usually what people do when it starts getting flaky.
So I don't know Lean, but in my experience with Coq is that when you fall to using liveness equality instead of definitional equality, then you're in a world of hurt because dependent types don't work right anymore.
Yes. So I have a slightly different perspective on that, which is that dependent types put you in a world of hurt, and if you can just use regular qualities everywhere and stay in simple types, then you'll be fine. So yeah, there are a lot of things I can say about that, but that'll probably take us off topic. But yeah, this is a major like practical sticking point. Like you do have to deal with definitional qualities especially when you're dealing with certain kinds of dependent types, and those can cause lots of issues. So yeah, I actually would try to avoid definitional, like relying on definitional equality when possible. All right, so Lean has a sort of obvious model of types as sets and elements of those types as elements of the sets. So we can write down a particular interpretation function where we just say, well, when you've got these for-alls, these are function types, and we're just going to interpret that as sort of a dependent function. Like ZFC has the ability to say, well, you've got a function, it's a bunch of ordered pairs, and then its domain is exactly alpha, and it's at x, it's going to be beta at x. So you just have these sort of dependent function types in ZFC, and you can write down what a dependent function is, and you're going to interpret universes as very large types. So the lowest universe is, because of the axiom of choice, we have law of excluded middle, we have proof irrelevance and all these things. We're basically forced to have prop look like that. So there's just two propositions. One of them is the empty set, which is false, and the other one is a singleton set, which contains this little thing I call the proof object, which is representing true, and the proof of true. And for the larger universes, we end up with these very large, so they have to be Grothendieck universes because they are closed under inductive types of various kinds, and also function types and all this. So they basically have to be inaccessible cardinals. So if you assume that there are n inaccessible cardinals, then we can define this thing. If we assume that there are omega inaccessible cardinals, then we can define all of them. But it's useful to consider the case where we just have n of them, and then we end up with this. So the soundness theorem is this, and it's so the main part is if E has type alpha, then you have an elementhood of the mapping, and if you have a definitional equality, then that turns into a regular equality in the mapping. And so Lean is consistent. I'm going to mention the overview of unique typing, but not the proof. Unique typing is this property here. We actually need it for in order to prove the well-definedness of that model, or of the mapping. So we need to know that there is a particular universe that every type lives in, and it doesn't live in any other universes. So that's to say that if you can derive that alpha has type universe n, then it doesn't also have universe m, where m is something else. So that boils down to this theorem, the unique typing theorem, which says that if E has two different types, then they are definitionally equal. And then you combine this and this rule here about inversion of definitions to say, so m is equal to n, and so there's only one universe that this term could live in. This is a little bit interesting in light of the undecidability results, that you can prove much at all about this typing relation, but you can actually prove this unique typing theorem, even in inconsistent contexts. This is false in Coq because of universe cumulativity. So there's possibly some analogous statement. I'm not sure exactly what that is. It would be quite difficult to state it, I think. Yeah, you can have universes switch around, and because of that, they aren't actually definitionally equal anymore. They're like, there's some subtyping relations. So it gets more complicated in Coq because of cumulativity. But this is true in Lean because we don't have cumulativity. And yeah, I'm going to skip the Church-Rosser theorem. But so I do want to talk about what's not here. I'd like to extend this a little bit to show some like concrete unprovability results. So for instance, that thing with the double equals, I didn't talk about double equals, but that's called heterogeneous equality. And one, I guess, folklore result is that heterogeneous equality is not, you can't prove that application preserves heterogeneous equality. Also, equality of types, you can almost never prove that two types are not equal. So for instance, you can't prove that int and nat are not equal to each other. Or even nat and nat prime, which is exactly identical to nat, where you just write down exactly the same constructors. You cannot prove that those two are not equal. You can prove that they are isomorphic, but that's the best that you can get. The only thing that you can do in order to really prove that two types are not equal is cardinality, because if two types are equal, then they have to have the same cardinality. But that's about it. Another interesting topic is what the VM does. So the virtual machine of Lean will perform some sequence of evaluations which kind of sidesteps a lot of the issues which the reduction relation that I've talked about. So when you have sort of casts from one type to another, Lean is just going to sort of ignore those. It's not going to evaluate the recursor down to a REFL. It doesn't care. And so it starts working through terms that are actually not well typed in the course of evaluation. And yet when it gets to the end, it somehow gets the right result. Like it doesn't go wrong. And so there's something interesting to show there. And so there's this concept of a type erasure map where you just sort of take out all the types and it's going to preserve the result of your computation. So yeah, if we did have something like that, one application of it would be a good theory for being able to show when a VM override is valid, which is a recent topic that we've been discussing, is the ability to sort of take one definition and replace it with another one in the VM. And then being able to do that without breaking, the results of it, of reductions, it would be very important. So having a good theory for that would be very useful. Strong normalization is another. Calling it folklore is, I don't know. but like Coq has various proofs of strong normalization of some subsystems of it. So I really like to have like the full theory altogether, strong normalization. I'm pretty sure that with the algorithmic reduction, it is strongly normalizing because it stops before it really gets into the weird stuff. Then, yeah, well, so this is a formal theorem prover, so this stuff should all be formalized. Okay.
All right. So the practice on these things is to usually start with the committee member who comes from the furthest distance. All the way across the audience. I think that.
Okay.
That is good.
How long do I have? So your answer to the understandability of differential equality, is it conceivable that there would be a more complicated way to do subsequent elimination, except the things you want to keep?
Well, so for the proof here, I use a different reduction, this kappa reduction, which one of its interesting properties is that it will actually do reductions even in that case where I showed, like here I'm showing, like when you take one of these ecrec terms, it'll reduce it like this. So it will reduce it even though it hasn't been given sort of any fuel to work with. And so because this thing actually contains a subterm of itself, this is going to run off. So this is going to, in that Turing machine example, this really will evaluate all the steps. And so it's not a decision procedure, it's a semi-decision procedure. So you can just run this thing, and then if they are definitionally equal, it will find it eventually. And that's about the best you can say with these sorts of things, because it is not a decidable relation. You can't have both decidability and like transitivity, or one of these other rules is going to break. You cannot have all of the rules because all of the rules together are not decidable. So if you want to have an under approximation, then you've got to give up one of the rules, or you live with a semi-decision procedure instead. And I think that in practice I wouldn't be so bad. I mean, having people sit at a prompt while the thing is humming and then eventually times out, like I think that would be fine for the purpose of definitional equality, especially because usually people write down proof terms that are actually correct, like that they've only put them into the big file because it's actually going to work. So we should feel comfortable just running them until they actually succeed, and that is just as good of a proof. So I would be comfortable with having a reduction which is more like this one, where it just does it does all the stuff, and it might not halt, but at least as long as you're giving it good proofs, then it will halt. So,
but if I kind of just going in there and say, oh, look, say I'm absolutely committed. I want to be decidable. So then, coming from that direction, what's the best you can do?
I think it would be best to eliminate Singleton elimination. So I think that.
And that's an all or nothing?
Even for equality?
Yes, that has some consequences. It might actually be recoverable in the case of equality. So you might be able to restrict sub-singleton elimination to things that look like ACK. So there are certain conditions that you can say about like equality is not recursive, for instance. ACK is recursive, and that's part of what makes this engine go, is the fact that it is recursive and it's just going to keep unfolding and unfolding. If it could only do that one step, then it would be okay. So maybe you can just say, yeah, you could restrict your rules on sub-singleton elimination to say, no, you don't get a sub-singleton elimination unless you're not recursive at all. And then ACK would be not sub-singleton eliminating, and that would affect some proofs, like your well-foundedness proofs would not be proofs anymore. They would be they would be regular types, and so that might affect some stuff. So I think that as far as damage to the ecosystem, I think that would be the least painful way to do it and recover decidability, which I think is important to me.
So related question with definitional equality. So as I understand it, you need that to get unique checker. Is that sort of minimal?
You need definitional equality to get unique. Well, if you
Yeah.
don't have definitional equality, you still get unique typing. It becomes an equality, right? If you don't have convertibility at all, it's just that if you don't have convertibility, then you kind of hamper your type system a lot.
Yeah,
Like,
okay.
so you have to, like, the result of that unique typing theorem can't be any better than definitional equality, because of course definitional equality implies that you can change the types.
Yeah, can it be anything less?
Can it be anything less? Well, yes, like in Coq, I think that they have something less. Like they have some kind of, it's probably like definitionally equal up to changing universes around in certain ways. The exact statement of that is not clear to me, but I think that you can say something like that. So there are other variations on this, I think, when the type system changes.
So like there's an eta rule for inductive types, right? You could either put that in or leave it out.
Well, if you took out the eta rule, then you can, I mean, you can still get some kind of result that says like, oh, these are, you know, almost equal for some sense of almost, and you just have to change that depending on the type system. So I would expect that most of these results continue to hold with variations if you change the type system in minor ways.
And I've sort of asked you this before, but what gets collapsed into the model? Like all empty types become the same, all crops become
Yeah,
the
so
same.
with this model, as I mentioned, we're just doing types of sets, and so all empty types are going to be treated as the same set. Now, you don't have to do that. You can actually tag types so that you get less collapsing, and that can be useful for trying to prove things like this this statement about equality of types only being disproved when the types of different cardinalities. You know, you can play with how you do the models of the types so that, you know, either you have just one type for each cardinality, and then you get a result like this, or you can say, well, you actually tag like the entire history of how the type was created, and that will show that you can consistently like distinguish all of these different kinds of types. So
The tag was actually a term in this.
the tag is some kind of term or like pseudo, like you might be able to replace things. You can replace things for equal things, like provably equal things. You always have to be able to replace them, so the model has to identify those. But anything less than that, like pi, like you can't confuse a pi for a universe. So that means you can give it a tag where pi's get one tag and universes get a different tag, and you can keep track of those tags so that you can actually prove that you can't ever.
I'm saying, do you think you can, are you speculating that something like this typing trip should work, or are you saying you know?
I have done in some extensions of this, which you can actually find on the repo. I've actually done this tagging business.
Okay,
So,
okay.
yeah.
Super good detail.
Yeah.
I'm sorry to keep
No,
interrupting.
that's good.
So, go ahead.
All right, so I have a few questions. So first, let me start with the one. So can you just define the word sub-singleton for me?
So sub-singleton meaning a type which has at most one element. So this is a funny terminology here, I guess, but the reason it's called sub-singleton elimination is because you can, as long as the constructors allow you to show that there's at most one element of the type, or at least it's inspired by this idea that you can show that there's only one way to inhabit this inductive type. And so because of that, all two elements of this inductive type are equal, and so it should be fine to treat it as though it were just a regular type, even though it's in prop and it's identifying all things. That's okay because there's only one thing there to begin with.
Now, is this in some deep way that escapes me the same usage of sub-singleton in proof theory?
What's the use of sub-singleton?
So in substructural logics, if you have at most one assumption, then that's called like a sub-singleton logic.
I mean, besides the use of at most one, I don't see a deep connection.
Okay, all right, so it's not the same word, it just happens to be spelled the same.
Well, I mean, it's the
Okay.
same. It's the same meaning.
Okay.
But I think I'll find it a different way.
All right, so towards the back of the thesis, you show how to encode the type theory of lean in another type theory where, let me back up. So one of the clunky aspects of lean, from my opinion, is the identification of prop with U0.
Okay.
Because then you need like the Imax, which is like max, but it's not quite max, and then there's like various things that propagate around where you have like this is the rule except if it's 0, and then it's something completely different. So at the end you show that well actually we could have set up the type theory so that prop and universes are two different things.
Yeah.
So why shouldn't that just be the type theory?
Yeah, so there's a big caveat about that reduction. So there's this proof splitting thing that you're talking about that's in the thesis that shows how you can sort of separate the entire logic into things where you have two different pi types. And one of them is just for proofs and one of them is just for non-proofs. The reason why that isn't good for lean as it normally is because of universe parametricity. So in this talk, I didn't talk much about the existence of universe variables, but actually the UNs, those are not just terms, or they're not just numbers. They're actually expressions that can actually contain Imax and these things in universe variables. And so you can have definitions which are parametric over all U. There are some definitions that are parametric over all U's which are greater than 1, or usually that's written like U plus 1 for all U. And so you can define these things which are sometimes props, and then those just propagate through the whole language. You can have all sorts of things that are sometimes props.
So that means you can cut back on code duplication then, right? So
Yeah, the
otherwise
idea
you'd have
is-
to write two versions of the thing, one
Exactly.
for prop and one for everything but prop.
Yeah, yeah.
But you could.
And I think that that's what Coq does,
But
right?
actually,
Yeah,
don't
Coq
think
has.
so. But
well,
but you could have the automation do this anyway without it being part of the type theory, right?
Yes. I'd be worried about potential exponential blowup. There are some cases where I
Are there
think
a lot of cases where you have a lot of different index variables in a single thing?
I mean, you can get 4+ in some statements. It's not that big of a deal, but and maybe it's comparable to the amount of difficulty just dealing with maxes of various kinds.